All right, this lecture we are going to look at you can read. It says analyzing graphs of quadratic functions. So the idea with this section is every quadratic is going to look like a parabola. And what we're going to try and do is we're going to try and get that quadratic. Remember what a quadratic function is. A quadratic function is f of x equals ax squared plus bx plus c, where a is not equal to 0. So if I have a quadratic like this, what we're going to see is that if you graph this, we will always get a parabola. Basically what this guy is going to be is it is going to be the graph of x squared just shifted around. We're going to do some transformations to the graph of x squared. And the hard part is going to be trying to get it into a form that is going to be useful for us. So what I want to do first is I want to just tell you what that form is, and then we will kind of see how we can take a function like this and put it into that form, and then we'll look at some application problems. So the standard, we'll call this the standard form. I don't actually know if it is the standard form. I think that's probably the standard form, but I'm going to call it standard form. So I'm gonna call this the standard form of, parabola, and that standard form. So f of x, and we're going to bring in some constants here. We'll talk about what those constants are going to mean here in a moment. And this is what we're going to call the standard form of a parabola, okay? Where basically what we're saying is this is a parabola, and here's all the possible things we can do to it, to shift it around, to stretch it, to shrink it, to move it left and right or up and down, okay? And if you notice, my parent function, if I asked you, what was the parent function for this? It would be x squared. And then there's some stuff we can do here, right? So this is a parabola. Its parent function is x squared, and there's some stuff here. So the h here is going to give us the horizontal shift, right? Depending on if h is positive or negative. In this case, because we're assuming h maybe is positive, it would be a shift to the right, or vice versa. If h was negative, it would become a plus, and so it would be a shift to the left. So that h is going to give us a horizontal shift. The a, right, let's talk about a. There are a couple things that can happen here. If a is less than 0, meaning if it's negative, right, then we reflect about the x-axis. And in this case, if that happens, we have what we call a maximum. I'm going to talk about that here in a second, okay? If a is greater than 0, meaning it's positive, we have no reflection, and so we have a minimum. Now, we also know if a is greater than 1, right, or the absolute value of a is greater than 1, then we have a stretch. And I'm going to put right here, if the absolute value of a is between 0 and 1, right, it's a fraction between 0 and 1, then we have a shrink. Okay, so this is what we mean by a graph like this, and what we're going to kind of define a couple more things here. So before we get too crazy, and what does the k do? K, right, is a vertical shift. So there is, if I can get my parabola, or my quadratic, excuse me, into this form, a lot of great things can happen. So we're going to come back to this. We're going to define some other stuff with this, but let's look really quick at an example of what could happen here. So for example, let's say I have f of x equals, let's just start off kind of easy, x minus 1 quantity squared plus 3, right? Well, we know that this has a parent function of x squared, right? That's going to be true for all of these. This minus 1 means that I shift to the right 1, and then I'm going to go up 3. So I know what the graph of this looks like. This is going to be, right, a parabola shifted to the right 1. So remember your parent function, your parent quadratic looks like this, right? So I'm going to undo that. Well, let's finish it really quick. There's my x squared, my normal x squared as a parabola, a bowl opening up. But now I'm going to go right 1 and up 3. Oh, I should have reconsidered how I made my graph. That's okay. Right 1 and up 3. And if I plug in a couple numbers, like if I plug in 0 and if I plug in 2, you're going to see that you're going to be at the 1. And here, if I plug in 0, I'll be up 1. which will put me at 4. Sorry, I didn't quite finish my thought there. And if you notice, I get this parabola. I really wish I would have done my axes a little different. That's all right. Couple things to talk about here. This point right here where my parabola opens up from, we are going to call this point, we're going to call it the vertex. And in this case, the vertex is 1, 3. It's opening up, right? Because we haven't actually reflected it or anything. I have no negative there. And then there's one other thing that we want to define, and that's what we call the axis of symmetry. So the axis of symmetry is basically going to be the line about which this guy has a reflection. So if I folded this guy in half, then I would have the sides of this yellow parabola meeting up or laying on top of each other. And so this is what we call, again, the axis of symmetry, because it's not a y-axis or an x-axis. I mean, it could be, I suppose, well, not an x-axis, but could be the y-axis if we haven't shifted it left or right. And then how do we describe a vertical line? Remember, a vertical line is described by x equals something. So in this case, this is a vertical line at 1, so we're going to call this axis of symmetry x equals 1. So a couple new terms. We have the vertex and the axis of symmetry. Let's look at another example, and then I want to add that back to our definition. Another example, what if we had f of x equals a negative 3 times x plus 2, and then let's do plus 1, okay? So what do I know? I know the parent function is x squared. I know this is to the left 2. This is reflected about the x-axis, right? So this guy's going to open down, and it's up 1, and it's a stretch with that 3, okay? So let's look at, just kind of go like this. That's great. So I know I'm going to go left 2 and up 1. So let's kind of try and make my coordinate system here something that will be useful to me. Okay, so again, I'm going to go to the left 2 and up 1. So I know my new vertex is going to occur right there. Okay, I'm going to go back and use yellow. I also know that this is going to open down, and I might just grab a couple x values just to see what's going to happen here. So look at, I'm at -2, so I'm going to pick numbers that are close to -2. Guys, okay, this isn't your fault because you've probably been yelling at the computer screen. Sarah, you forgot you're squared. It's not a parabola, it's a line. Sorry about that. There's the squared there. So if I put in my -1, I get 1 squared times -3 is -3. -3 plus 1 is -2. And if I put in, give me another point, close to -2, -3, you're going to see you'll get the same thing. So if I get that -2, let me give myself a little bit more room here. Okay, so I'm going to graph this guy, and it's going to open down. I know it's a reflection about the y-axis, and I plugged in a couple of points, and I saw that that was true. And the interesting thing, and look at this guy, so you just make that point a little bit bigger. Because it's multiplied by 3, it's really not going to be quite as wide as a regular one. It's going to be kind of skinny. So what is our vertex in this case? Notice my vertex then is a -2, 1, right? What is my axis of symmetry? My axis of symmetry is going to be this line right here, which in this case is x equals -2. It's always just going to be the x value of your vertex. Okay, that'll be your axis of symmetry. Listen, if you put -2, that's wrong. If I ask you what is the axis of symmetry and you say the axis of symmetry is -2, -2 itself isn't a line, right? I need a vertical line. When you say -2 equals x, now you've described a vertical line to me. So make sure you're putting that. A couple other things that I just want to talk about that are interesting about these graphs. If you notice here, this graph up here has a minimum, right? If you look at this graph, what is the smallest y value that this graph hits? Does it hit a smallest y value? It sure does. What is the minimum? The minimum is 3. Whereas in this case, if you look at this parabola here, this guy has a max, right? I have a maximum. So this guy has a max of 1. So that's all the stuff that just by being able to put a quadratic in this form like that, we can tell all of these things. We know if we have a maximum or a minimum value, and that's always a y value. We know what our vertex is, kind of where it starts, and we know its axis of symmetry. So let's go back to our definition here, and let's add a couple other things to this. So right here, we know we have a max. Whoa. Yeah, I know. We have a maximum, right? And the maximum value is going to be the y value of your vertex. Here we have a minimum, and this would be the y value of your vertex. Oh, and I haven't actually said what is our vertex. Our vertex in this case, look at what I've done. I've shifted it to the right h and up k. So our vertex is always going to be h comma k, and our axis of symmetry is going to be x equals whatever the x value is of your vertex. So the y value of your vertex gives you your maximum or minimum, depending on if you're opening up or down. And then your x value of your vertex, if you put x equals that number, that's going to give you your axis of symmetry. Okay, so good times. All right, so let's look at how do we get it into that form. So these guys were already in that form, but how do we get there? And we're going to come back to that lovely method of completing the square. So I want us to find the vertex, axis of symmetry, maximum or minimum value. We're going to do a couple of these. So, and then the other thing that's kind of interesting to talk about is let's find the intervals over which the function's increasing and decreasing. Oops. Intervals. We've done that before, right? Of increasing and decreasing. Okay, so those are all the things I want. I want the vertex, axis of symmetry, the maximum or minimum value, and the intervals of increasing or decreasing. So let's start off kind of easy. Let's say that I have f of x equals x squared plus 6x. Okay, now I could graph this. Of course, this is a parabola. Okay, it's going to look just like x squared, just kind of shifted around a bit, right? So what I want to do is I want to be able to get it into standard form. And remember what standard form is, right? Standard form is a times x minus h, and I might not have that a, and that's okay, plus k. That's my standard form, and that's my goal. So I want to get a perfect square polynomial, just like we did before when we solved quadratic equations using completing the square. I'm going to do kind of the same thing here. So how do we complete the square again? So what I'm going to do is I'm going to take half of that middle term. Remember, half of 6 is 3, and then I'm going to square that sucker. And when I square that, I'm going to bring that in, and that's going to be what I'm going to use to complete the square. So what is it? 3 squared is 9. Now, here's the thing though, you guys. So I brought in that 9. In the last section when we did this, what we did to one side, we did to the other. Well, now I don't have the other side. There are ways that you can do the other side if you want to use those ways you can. I don't like teaching it that way because I feel like it confuses my students where maybe I add the 9 over here and then I bring it back over. So what I just want you to look at is look at what you've brought into this function. I've brought in this plus 9. Remember, what was my original function? My original function was this x squared plus 6, right? So I can't just, I've totally changed the function by bringing in that 9. So a great trick in mathematics is, well, I want that 9 there. I have to bring it in, but let's just take it away over here. So I put these parentheses. That doesn't change anything. Notice if I simplified this, guys, I would have x squared plus 6x plus 9 minus 9, and my 9s would cancel, and I'm left with my original function. Isn't that a great trick? Great trick in mathematics is if you want to bring in a 9, but it's not there originally, just take it out also. And now why did that, why did that help us? So why that helped us was now that I've completed the square, remember this guy right here is a perfect square. This is x plus 3 times x plus 3. Remember, it's always going to be that number right there. And then this minus 9 just hangs out. And whoa, that was crazy. And what is so great about that is that now we have it in this form. And I can easily see what my vertex is. I can see that this is a parabola opening up. I can see that it's going to have a minimum value then if it's opening up. And I can just look at that and know there's a bunch of cool stuff going on there. Again, if you foil this out, make sure you agree that this is the same thing that we started with, right? Whoops, I don't need the squared here. So let's FOIL this out and make sure we get what we should get. If I FOIL this, I get x squared plus 3x plus 3x plus 9, all minus 9, those 9's go away and I get x squared plus 6x, which is what we started with. So that's what we want. That's what we want to do. All right. So what do I know here? What I like to do with this, you're going to get it into standard form and then you need to answer all of these questions up here. So what I like to do is just make a quick sketch of this. I know that this guy is shifted, right? I know what this guy does. I know it's shifted to the left 3 and down 9. Look, I'm not even making this perfect. I'm just going to draw myself a quick sketch so I can see, oh yeah, okay, I have, oh, why did I, are you yelling at the screen right now? I'm so sorry, it's opening up. Oh, and does it go through, let's see, if I put in, yeah, that's kind of interesting. Left 3. When x is 0, oh, it goes through the origin. That's great. That's really interesting, but it doesn't really matter, especially because my graph is so horrible. My graph is so horrible, but I do a quick sketch of it. So now what can I see? I can see that my axis of symmetry, pretend that that's symmetric. Just pretend, people. You can pretend. That's all right. So what's my vertex? My vertex is -3, -9, right? I can see that just by knowing this shifts to the left 3 and down 1. So that's my vertex, okay? My axis of symmetry, my AOS, if you want to sound cool, which I know you do, remember is x equals a -3. It's a vertical line that's through the vertex, okay? What else do we need? A maximum or a minimum value? Has a minimum. What is the minimum? What I'm talking about here is I'm talking about the y value, okay, has a minimum of -9. What does that -3 have to do with it? Well, it tells us where that minimum occurs, okay? So maybe I have a business and I'm looking at a profit function, and while I might care that, you know, my profit, my minimum profits in August, I also care what is that minimum profit. In this case, that doesn't make sense because I have a -9, but I guess we could be losing money. Oh, that's kind of sad. Let's look at what this guy's doing. What are we doing? We're going to be decreasing until -3 and then increasing. So where am I decreasing? I'm decreasing from -infinity to -3. Remember, we never put closed parentheses when we're talking about increasing and decreasing, because I can't be increasing or decreasing at a point where I switch, right? Going from decreasing to increasing. And I'm done. That wasn't too bad. Not too bad, huh? I guess you could argue it's not too good, but it's not too bad. Let's do another one. Whoa. I was trying to save my instructions there. That didn't work very well, did it? Okay, so let's look at another one. Let's do one that's maybe a little bit more complicated. Maximum or minimum value. Oops. Okay, so let's look at f of x equals, let's stay kind of easy here, 2x squared. I want to do minus 8x plus 1. Okay, so right away, one thing that you are going to notice is that you're going to have a minimum value, okay, because I have a positive number in front of that x squared term. But what I want to do, again, I want to get it to this guy right here, and to complete the square, I must have a 1 in front of the x squared term. So what I need to do first is I need to factor out that 2. I'm going to take a 2 out of this quadratic right here. Now I only need, when I complete the square, I only need the x term. So I'm actually just going to put a parenthesis, give myself some room because I know I'm going to bring in a number here, and I'm going to put a plus 1 out here because that 1's not going to help me complete the square, okay? So I'm ready to complete the square. When I go to complete the square, what I need to do is take half of that middle number, square it, and then add that to both sides, right? So half of -4, what is half of -4? That's -2. -2 squared, this one's kind of nice because it's pretty easy. -2 squared is a positive 4, right? I get -2 times -2, and I get a positive 4. So I'm adding in that 4. Now remember, we have to be very, very careful when we are bringing in that number. Before, all I did was I brought in the 9 and I took the 9 away. In this case, though, we have to be a little bit careful because if you notice, this 4 is in this whole set of parentheses. And what is this whole set of parentheses being multiplied by, you guys? It's being multiplied by 2. So what I didn't actually bring in a positive 4. What did I actually bring in? I actually brought in a positive 4 times a positive 2. So what did I actually bring in? Sometimes I'll do a little, I know this is kind of silly, but I'll do a little bit of work on the side here and I'll say, okay, what is 2 times 4? It's 8. I know that's kind of silly, but we're going to get to bigger numbers, so that might help a little bit. So what did I actually bring in? I actually brought in a positive 8, so I need to take that 8 away, right? I have to make sure that I don't bring in anything the extra, right? I need to make sure that whatever I brought in, I take it away so that I continue to have the same function that I had up here. I can't change the function at all. I can make it look different, but I can't change it. I don't know if that makes any sense. But let's see what happens here. So this guy right here is going to be a perfect square, right? It's going to be x minus 2. That's, what did I square, right? I squared negative 2, quantity squared, and then 1 minus 8 is minus 7. And look how beautiful this is. Now I have this quadratic. What do I know has happened to this? It's been shifted to the right 2 and down 7. So it's shifted to the right 2 and down 7. I don't really care where. I just want to make it so I can graph this guy, right? Something like that. And so what do I know? I know it has a minimum value. Well, let's talk the vertex first. Vertex then is going to be to the right 2, so positive 2, down 7, so negative 7. What is my axis of symmetry, right? My axis of symmetry is going to be a line that goes through that point right there. So I need to write it as a line. So it's x equals 2, okay? Again, I'm going to have a minimum value here. So what is my minimum? My minimum is negative 7, right? And then intervals of increasing and decreasing, same thing. I'm decreasing from minus infinity to 2, and then I'm increasing from 2 to infinity, okay? I hope that makes sense. I want to show you up here, once again, why did that work? Why did I subtract 8 and not 4? Look at if I simplify this, you guys. Let's take the 2 through. I would get 2x squared minus 8x plus 8 plus 1 minus 8. Look at those 8's cancel, and I'm left with the 2x squared minus 8x plus 1, which is exactly what I started with, which is exactly what I need to end with, right? If I simplified it all out. Again, this form right here, FOIL that all out. FOIL out that x minus 2 squared. If you FOIL that out, take the 2 through, simplify everything, you best be getting what you got up here, okay? Let's do one that's maybe a little bit harder. Oh, that was part B. I shouldn't have. Whoops. Because did you feel a little bored with that? I know I don't want you guys to be bored. We have lots of fun examples that we can do. So let's look at another one. I don't know. Let's bring in a negative and maybe a fraction. How about that? So this is going to be technically part C, right? Part C. All right. So let's get crazy. Let's say we have f of x equals how about a negative 1/3 x squared minus x plus 2. Oh man, we're getting crazy. Okay, but we're not scared. This isn't going to be, we can do this. So let's, again, I just need the first 2 terms to be able to complete the square. To complete the square, I need to have a 1 in front of the x squared term. So I'm going to factor out a negative 1/3. Take that negative with you, okay? Take that negative with you. So I have an x squared. Now remember, I'm factoring it out of this, just these first 2 terms. And also remember that factoring really just means division, okay? So really what I'm doing is I'm dividing these first 2 terms by a negative 1/3. Clearly negative 1/3 divided by negative 1/3 is 1. That's how we get a 1 right there. And now if you don't see what your answer is going to be when you divide this guy, let's do a little bit of side work. What is the coefficient in front of x, in front of that x right there? It's a negative 1. So I'm going to take a negative 1 and I'm going to divide it by a negative 1/3. So remember, when we deal with fractions, we flip the denominator and multiply, right? So look at what we get here. I actually, negative times a negative is a positive. So I actually get 3, which kind of makes sense. Like think about, that's asking how many thirds are in a whole. There are 3 thirds, and because it's 2 negatives, we get a positive, okay? The other way, make sure you, how can you check yourself and make sure you did that correctly? You can always go and take that negative 1/3 back through, right? And you better get back what you started. You better get back what you started, people. Okay, I'm going to leave myself some room here, and the 2 is just going to hang out here because the 2 doesn't actually do anything yet. It doesn't do anything to help me complete my square. It will eventually, I'll need it for my vertex. But all right, what does it mean to complete the square? I'm going to take half of the middle term, half of 3. Don't put 1.5, put 3 halves, and then I'm going to square this guy, right? So what do I get when I square 3 halves? I get 9/4. Now this one, we were crawling and now we're running, but that's all right. Follow me. You can follow me. So if I square that, I get 9/4, right? Now again, I'm not going to take away 9/4 because I didn't actually bring in 9/4. What did I actually bring in? I actually brought in 9/4 times, right, the -1/3. Okay, because this 9/4 is trapped inside these parentheses, that means that it is being multiplied by that, let me get rid of that, -1/3. So this is where I do a little bit of side work, and I would recommend it too. Don't try and do this in your head. What did I actually bring in? I actually brought in -1/3 times 9/4, which that 3 can cancel, right? So what did I actually bring in? I actually brought in a -3/4, right? That's what I actually brought in. That's what this number is, times the -1/3. So if I actually brought in a -3/4, I need to counterbalance that with a +3/4 out here. Guys, take the -1/3 through, take that time to multiply the -1/3 through, make sure everything cancels, and you should get this guy back out, right? That is what should happen if you did it correctly. Okay, cool. We are cooking with gas now, people. So that -1/3 stays right there. Because I brought in that 9/4, that makes this guy right here in the square a perfect square. And remember, it's going to be x and then whatever I squared, or half that middle term. Okay, so it's going to be x plus 3 halves, quantity squared. Let's get a common denominator here. I'll multiply this by 4/4, right? So 8/4 plus 3/4 is 11/4. Okay, I got it in there we go. We're good to go. I have it in my standard form. I'm ready to go. What are some things I know about this graph? I know it's been shifted to the left 3 halves and up 11/4. So left 3 halves, right? A little bit, and up 11/4 is like almost 3. And then what do I know about this guy? It's going to be squished a little bit. Squished isn't the term. It's shrunk. I'm going to have a shrink. Okay, so it's going to be a little bit fatter, and it's going to open down because it's had a reflection about the x-axis. Okay, so right away at looking at this, I know that this has a maximum, right? I could have seen that this was going to have a maximum up here. Anytime my negative is in front of the square term, I know I'm going to have a max. Anytime the number in front of the square term, the coefficient of the square term is positive, I'm going to have a min. So what is my vertex here? Well, it's to the left, right? So my vertex is a -3 halves, 11/4, moved up 11/4. Axis of symmetry, again, is that vertical line that is running through that point right there. So that would just be x equals -3 halves. This has a maximum value. How exciting. What is the max? The max is 11/4, right? That is the biggest number that, or function value that the function takes on. And then intervals of increasing and decreasing, this one's a little bit more interesting because we see that we're going to actually go from increasing from -infinity up to that x value, which is a -3 halves, open, and then we're decreasing everywhere else, -3 halves to infinity. Okay, so I go from increasing and then I go to decreasing. When you get to calculus, it's pretty fun because you can see all this about the function just by taking its derivative, which is great and so much easier. But we don't know calculus yet. That's just a little tease for someday when you're gonna get to calculus. Okay. That's kind of what we're gonna do with those. Finding the vertex, axis of symmetry, max or min, intervals of increasing and decreasing. There are ways that you can memorize formulas so you can find the vertex every time and you don't have to go through with completing the square. I want you to complete the square though, sorry. So instructions will say, complete the square to determine the following, and you need to complete the square to do that. So if you don't use completing the square, then you won't get the full points if you just memorize the formula of, the negative b over 2a. Not that it's bad to memorize formulas. Sometimes it's important to memorize them. Of course, quadratic formula we use so often. That's something that you need to memorize. But I don't know about you, but I went through all my whole math career never memorizing the vertex of a parabola formula. And I could always just get it from completing the square, which takes like 2 more seconds, right, to do that. Well, maybe not 2 seconds, maybe a little bit longer than that, but it's a fun, 30 seconds of whatever you're going to do. So I just want you to realize that. I don't want you to memorize the formulas. I know the book gives you that formula for the vertex of a parabola. Please don't use that. Please make sure that you're using completing the square to find all of these solutions, like the vertex and all that good stuff. All right, last part of this lecture, and the most fun part, of course, are applications. So the great thing is when you get a quadratic into the form, the standard form that we have there, we know it has a maximum or a minimum value. So this leads easily to finding applications, to figuring out, can I solve things that involve like finding a maximum or a minimum, okay? So let's look at, I'm just gonna grab one of these out of your book. Let's just do a couple applications and then we'll call it good. So here is one. A stone is thrown directly upward from a height of 30 feet. If you've had any physics, you'll recognize the equation I'm going to give you. So some of these are easy because the equation is given to you. Some of them are not as easy because the equation is not given to you and you have to figure out what that is. It's with an initial velocity. All this stuff that they're telling you right here isn't actually stuff that you're going to need to know, but they're just kind of describing how they get that equation with an initial velocity of 60 feet per second. Right, velocity is a rate of change, okay? The height of the stone in feet, I'm just gonna, obviously it's the stone. Let's say the height in feet, okay, t seconds after being thrown is given by oh my goodness, so much writing. All right, so is given by this function, s of t. S a lot of times in physics and stuff is for displacement, or, we could have used h too, but negative 16t squared plus 60t plus 30, okay? So the question is, determine the time well, actually what I want you to do is I want you to determine the maximum height of the stone. I'm just gonna put the max height, I'm being lazy. Words, right? The max height and the time it occurs, or how long it takes, right? How long does it take to reach its maximum height? All right, maximum height. So here's what we got. We have this function that we're given. So half the battle is understanding what the function gives us. What this function gives us is, we throw a stone, and if we put in a t time after it's been thrown, it spits out where that ball is, the height of the ball. Notice if t is 0, we get 30. That makes sense because that was the initial height of the ball. So maybe you're standing on, I don't know, the top of a roof and you decide to throw a stone and really hope that there's no one underneath you. But what I want to find then, the idea here is that I have this function and I want to find the maximum height. The good thing is I know that this is a parabola, right? And I know it has a maximum because of that negative 16. So right away I want to get this into a form that is useful for me, and that is going to be standard form. So I'm going to take out that negative 16. I'm going to do a little bit of side work, right? What does it mean to take that out? 60 divided by a negative 16. Well, that's not going to go in evenly, but I can simplify this a little bit, right? I think I can take a 4 out. If I take a 4 out, I get 15 fourths, and that is negative. So again, a little bit of side work just so that I don't mess up. So if I divide 60 by 16, I get a negative 15 fourths t. And then I'm going to leave myself some room, and I'm going to have the plus 30. Again, completing the squares so that I can determine the vertex, which will give me the maximum, and where it occurs. Okay, now I'm ready to complete the square. Same thing every time. I'm going to take half of a negative 15/4, which in this case is a negative 15/8. We're going to get into some serious fractions here. So in this case, I would probably, I mean, if you wanted to use some decimals, I would support that because, you know, like when we talk about time and stuff, a lot of times we don't talk about it as like, you know, oh, it occurred at 15/4 seconds. We would probably say, you know, that occurred at 3 3/4 seconds or something, 3.75 seconds. So if you wanted to go to decimals at this point, that would be fine. So what did I bring in? Did I bring in 225/64? I actually did not. What did I actually bring in? I brought that 225/64 times 16. So negative 16 times 225/64. 16 goes into 64 4 times. So I actually brought in a negative 225/4. So what's the opposite of a negative 225/4? It's a positive 225/4. Do you see how I'm figuring out what I brought in just by doing a little bit of side work here? Okay, so S of t then in this case, I'm ready to go. I have a negative 16, that's good. That negative tells me it's a maximum. I'm gonna have t minus, what did I take half of? What did I square? Was that negative 15/8? So I get t minus 15/8 squared. And then if I get a common denominator, times that by 4, times that by 4. That's 120. I don't have a calculator on me. So what's a math teacher without her calculator, right? 345. She's still a math teacher. 345. That's cool. All divided by 4. But I do, however, have a handy dandy phone with a calculator on it that I can figure out. All right, so guys, look at what this tells me, right? Remember what this function is. If I look at my vertex is, this is shifted to the right 15/8, right? And it's shifted up 345/4. So I know my vertex, right? And this opens down. So I know that this guy is shifted to the right and up, and it opens down somewhere. Okay, good enough. Has a maximum. So remember what this is. This is going to be my time. Your input is time, your output is height or your feet, right? What did the question ask for? Determine the max height and the time it occurs. So the maximum height, if I divide that out, I'm running out of room here, I would write this in a beautiful sentence, is 86.25 feet. That's my maximum height, okay? And where does it occur? It occurs at this time value right here. So almost 2 seconds, right? 1.875 seconds. This is horrible. Sorry. You would write this in a beautiful sentence, right? The maximum height of the stone is 86.25 feet, and it occurs at 1.875 seconds after being thrown. Does that make sense? I hope that makes sense. Let's do one more application problem, and then I've probably lost you since we're almost at 40 minutes here. Let's do one more application problem where we have to kind of set up, the problem ourselves, okay? So, real life here, a rancher, right? How many of you are going to become ranchers? Some of you probably. Needs to enclose two adjacent, so that's next to each other, right? Adjacent, sorry if I spelled that wrong, rectangular corrals. One for like cattle and one for sheep or something. I don't care what the rancher is going to put in the corrals. I just know I need two corrals. If a river forms one side of the corrals, so we'll draw a picture here, and 240 yards of fencing is available. Real life. How many times have I been like, man, I need to build my two rectangular corrals next to the river, and I don't know how to maximize my area, right? Is available. What is the largest total area that can be enclosed? What is the largest total area that can be enclosed? All right. So steps of problem solving, right? Read the problem, read it again, read it a third time, and then figure out what is important in the problem maybe and what isn't as important. So let's draw a picture here. Oh, guys, I have different colors. So here's my river. River, isn't that a beautiful river? And I kind of love that we're building a corral. So 2 rectangular corrals. We're building 2 corrals, right? We don't know what size they're going to be. Doesn't really matter. But we do know that whatever we put in the corrals can't swim, apparently, because it's totally fine that we're not going to have any fencing along the river. So whatever we're going to put in these corrals, they can't swim. So the trick with a problem like this is we're going to kind of go back to where we, had 2 equations with 2 unknowns, kind of like what we did in the last section where we did applications, but now we're going to have a function instead. So I'm going to define this a little bit. I'm going to call this length right here y. So this would be y, this would be y, this would be y. And then I'm going to call this whole length here x, okay? And what do I know? So what is given in this case, right? I know that I have 240 yards of fencing. So let's add up all the fencing that I have. I know that x plus how many y's? 1, 2, 3. 3y must equal 240. That's what I know, you guys. I know that I have that much fencing. What do I want? I want to find the maximum area. So I want the maximum of, now let's find a function that describes area. Area in this case, right? I want the area of the whole thing, not just each one. So let's consider, it said the total area enclosed. So that area is just going to be this x times y. I want to find the maximum of a, which equals x times y. What's the problem though, right? The problem is that this is in 2 variables. Well, I can do this pretty easily. Let's solve this for x. That says 240 minus 3y is x. So what can I do then? I can rewrite my area equation in terms of just 1 variable. In this case, it's just going to be in terms of y. Remembering y is just one of our sides. Okay, so if x is 240 minus 3y, then I'm going to replace this x right here with that 240 minus 3y. That's all times y. If I rewrite this, that'll be a negative 3y squared plus 240y. I want to make this into something that I can use. All right, you guys, so now this is a parabola. I know this parabola is going to have a maximum because of that negative. So let's take out that negative 3. That leaves me with a negative 80y here, right? Positive 240 divided by a negative 3 is a negative 80. And now I'm ready to complete the square and see what I have. So I'm going to take half of negative 80. Half of negative 80 is a negative 40. And now I'm going to square it. So when I square a negative 40, I'm going to get a positive 16 with 2 zeros, right? 1600. Okay. What did I actually bring in? Again, what did I actually bring in? I brought in 1600 times negative 3. So if I do a little bit of work somewhere, negative 3 times 1600, right? That's going to equal negative 4800. So what is the opposite of a negative 4800? That would be a positive 4800. These numbers make sense, right? We're talking about area of my corrals for my non-swimming cows and sheep. Maybe they don't swim. I don't know. I'm not a rancher. So someone out there is probably like, yeah, duh, sir. If you put up next to a river, they're not going to go across the river. I don't know. All right. So look at what we have. So what do I know about this parabola, right? It's shifted to the right 40 and up 4800, way up here. And it's opening down. That's good. And remember, what is my input in this case? My input is that side y. What is my output? My area. So guys, when you look at your vertex here, your vertex is 4800. Remember, what is this input? This input is y. That's this side right here. And what is the output? That's my area. So what is my solution to this? What is it asking for dimensions? What is it asking for? It's not asking for dimensions. It's just asking what is the largest total area. So my answer in this case, I'd put it in a nice sentence. And I would say that the largest area that can be enclosed is 4800 square feet. Not feet. Nope. Yards. Square yards. All right, we are almost at 45 minutes, and I imagine you have had enough. These problems can be tricky. I need you to look at the fun sheet and look at examples in the fun sheet. And if you have questions, of course, ask me, because we only did 2 application examples. So please look at the fun sheet, work on the homework, and let me know if you have any questions.